So here's the, yeah, so I was saying these are, we're gonna talk about equation for a line, but this is specifically parametric equations, right? Like you've learned about different types of equations for a line in the past, right? Like y equals ms plus b, point slope form, stuff like that. But this is gonna be a parametric equation, which means, as you can see here, the start here is we have L of t, right? So L is just like the name for our line, and t is what we would call a parameter, right? Because it's like this extra variable that's hanging around. That's not x, y, or z. So it's this extra parameter. So we'd call t, t is a parameter. Parameter. So that's why these are called parametric equations. And the way we do this, so I also left out, so this is, the information you need to be given is a point and a vector, okay? And we'll see how to do it with slightly different information too, but basically you're gonna want to get to the point where you have a point in space and a certain vector direction. But the point, I'm gonna need to give a name. So let's say the point's name is a point, oh, no, I did give it a name, a point A. This should be a vector here. So this should just be a point A, which is a vector in the v direction. So you have a line through the point, which we call A, and it's going in the v direction. So the equation for this line is you start at A, and then you add t times v. Okay. So this is kind of, this is going to be the equation for the parametric equation for a line in the through a point in the v direction. Okay, so how do we want to think about this? Oh, I guess if a might not be technically a vector, so I guess a is a point. So I keep going back and forth, but remember yesterday we talked about how point you can think of as a vector that's pointing, like going from the origin to that point, right? So you can consider vectors and points basically the same thing. But I'm going to draw a little picture here, which should hopefully help clear up that distinction there and why I had a little vector symbol there. Even technically, I shouldn't have. So if you're given a point, let's say this is our point here, A, and you're given a direction, V, you want to draw the line through this point in that direction. So let's draw that line here. I'm going to draw it in a different color. Okay. So you have something like that there, right? And you have this V direction, right? So the question is, how do I get an equation for everything you see here in blue in terms of A and V? Okay, well, the reason that I was thinking of A as a vector is because, well, I could just put, just like look for the origin. This is living in 2 or 3 dimensional space. Look for the origin somewhere. The reason we look for the origin is because when we're thinking of vectors, we always think of them based at the origin. And so you think of it at the origin, and you could think of A as this vector that starts at the origin and points at this point. Okay. And now you could see, if we want to add, or if we want to get to any point here, we just have to add a certain vector. For example, this point here, maybe I'll use a different color. So this point here, right, is just the vector given by A plus V, right? That's this. So maybe this vector here, I can call it the vector A, and so this is the point A, and then this is the vector A, which point is just the point, the vector pointing at A from the origin. Okay, all right. So that's what we talked about a little yesterday, the difference between a point and a vector. Right, but basically what this is basically doing is consider A as a vector, so it's a vector going from the origin to here. This point here is A plus the vector. If we want to get any other point, basically all we have to do is we could either squish V. So for example, here I need different colors. This point here, you could think of as like A plus, well, it's not V, but it's just a scaled down version of V. So maybe like half of V. And something out here would be like A plus 2 times V. And something over here, what would this one be? What would the point over here look like? A A minus V. Yeah, so like A minus V, or in other words, A plus -1 times V, right? Right. So A minus V or A plus negative, you plug in T equals -1. So this is like T equals 1/2. This here is T equals 1. This is T equals 2. And this is T equals -1. Right? So basically what this equation is doing is it's just saying, okay, you have a point A, you have a vector coming off of it. All you do to get the rest of the line is you just scale that vector up, right? Or flip it in the other direction, or squish it down, right? You're just scaling that vector or flipping it and scaling it in the other direction. So it's negative, right? So you're just, basically you're just taking some real number, scaling the vector and adding that onto the point. Okay. So conceptually, this is the picture that you should be thinking of. You have a point, think of it as a vector so that you can do vector addition, and then you just add the other vector, and you get different scaled versions of that vector, and you get the whole line. Now this equation is nice and simple. Like, it's really easy to look at, but it's not as easy to work with, because in the real world you're probably going to have coordinates and stuff. So for example, if A, let me change back to plain color. So if A equals, let's say XYZ, and V is some vector, let's say V1, V2, V3. Right, so let's say we have these two things. Maybe actually I shouldn't call this XYZ for reasons we'll see right now. Maybe I'm going to call this A1, A2, A3. Okay. So this is kind of our setup. This is a parametric equation. Again, this is working in 3D. It would be very similar in 2D. You're going to hear that sentence a lot, right? You heard it a couple times yesterday. You're going to keep hearing it. I'm often going to do things in 3 dimensions that could just as easily be done in 2 dimensions. And so it's like technically a similar equation for the version in 2 dimensions. But this equation here, which is like compact and nice, you can like spread it out, and you can see like what's actually going on here. And this is actually a collection of 3 equations, one for each component. So you can say that L is given by this triple of equations. So X equals A1 plus TV1, Y equals A2 plus TV2, and Z equals A3 plus TV3. Okay. So this tiny little equation is actually these 3 equations all put together in vector notation, using vector notation. Okay, so this is easy to look at in like a conceptual way. Like, it's just like, it just condenses all of the information very nicely. But when you're actually working with a concrete problem, you're gonna, like, the point isn't just gonna be a letter. It's gonna be an ordered triple or an ordered pair, right? And the vector is also not going to just be a letter. It's going to be an ordered triple or an ordered pair, right? And so you're going to have all of this information. And this doesn't necessarily give you a lot of information in terms of this. If you do all the, this has become scalar multiplication, and you do vector addition, and you basically get the same thing. Yeah. So you can think of it also like a kind of combining these 2 ways. You can think, okay, L of T is equal to the x coordinate or x in the x coordinate, y in the y coordinate, and z in the z coordinate. So this is, again, just a third way of looking at it. But this one is not, I don't think, too much of a stretch, right? It's just plugging this in for x, y, z, right? So you're going to see kind of these two different ways of writing things. Sometimes you'll see something like this even. But in the homework, I think it looks like mostly when they give you a line, they're going to give you either this or they're going to give you this, right? They're going to give you one of these equations. Okay. Cool. Any questions? I think we're going to do some examples now, so just be prepared for that. Okay. Okay. Cool. Okay. So here, again, if you need me to slow down, let me know. But we're going to jump into some concrete examples here. So here's a couple of questions asking us to find some equations for lines. Oops. There you go. Okay. So let's start with number 1 here, which is to find an equation for the line through this point, 2, 1, 3, in this direction. So as you can see with our setup over here, you can, can you not see? Oh, what just happened? That's funny. Okay, let's see what if I just close that warm up. There you go. Yeah, that did it. Cool. You can see now, everyone? Yeah, I'm trying something new. It wasn't working yesterday, but it was working when I tried it just now, and hopefully it keeps working. Okay, cool. So as you can see with the setup that basically is the most ideal setup is you're given 2 pieces of information, a point and a vector. If you're giving those 2 pieces of information, you can just use this formula here, or one of these sort of versions straight away, right? You don't need to really do any extra work. You can think of it conceptually, right? You're like, you should have a picture like this in your head of what's going on here, but you can jump straight to just using this formula. So using this formula, we can get a nice equation, something like, so we always want to start like, okay, L of t, or we can give the like x, y, z, either way you want to do it. I'm going to do like something like this formula here. So, right, A1, A2, A3, what are those? Those are the coordinates of the point that's been given. So in this case, that's 2, 1, 3. V1, V2, V3 are the coordinates of the vector, the direction we're pointing. That's these three coordinates here. So basically, this is going to be A1 plus T times V1. So that's 2 plus T times 1. And then 1, that 1 is coming from right here, this 2, 1, 3. And then plus T times V2, but V2 is 0, so that's just going to be plus 0. And then 3 is, the third coordinate is A3, which is 3 plus T times V3, which is also just 1. And that's it. That gives us the equation for the parametric equation for that line. You could also write it as x equals 2 plus t, y equals 1, z equals 3 plus t. Right, those are equivalent. Okay. Okay. So now this next one is a little different. This one, we're not given a vector, right? And so now this is where I want to highlight something, right? Before I even start doing this problem, because first of all, this one we're just given 2 points, So you know this problem is going to be a different setup, because what I taught you was if you have a point and a vector, and this one just gives you 2 points. So what do? Well, conceptually, we know that if I give you 2 points in space, there should be some line that goes through them, right? So it should be possible to do this. The question is just how do we do it? Okay, and we'll talk a little bit about that in a second. But second, I want to talk about, just like like test taking strategies / homework solving strategies, right? When I write these problems myself, it's pretty clear what version you're getting, right? You're getting in this first, in number 1, you're getting a point and a vector because I use the different notation. And in number 2, you're getting 2 points, okay? But as you remember, I mentioned yesterday, the homework and the textbook like to use parentheses for both points and vectors. They like to use them both kind of interchangeably. Because of that, you're always gonna see parentheses when you're looking in the textbook or on the online homework, and so you have to be sure to read the questions carefully to make sure what version of the problem you're getting. Are you getting a point in a certain direction, or are you getting 2 points? Okay, so it's important that you see that you look for that difference. Okay, so in this case we get 2 points, and we're asked to write an equation for the line, but connecting those 2 points. Again, conceptually, if I give you 2 points, you should be able to draw a straight line between them, right? And the way we do that is, well, we need to come up with a vector that starts at one point and goes towards the other point. So let me just draw a little picture over here. So you have 2 points, let's say P1 and P2. And we want to draw the line that connects them, right? So try my best. That isn't great. So there you go. So this is going to be our equation. This is going to be our line L. And the question is, well, I know I have these 2 points. I need a point and a vector in order to use the formulas that I've been talking about. Well, why don't I just shouldn't there be a way to give me this vector right here? Okay. Right. Hold on. This vector right here, right? And the way we're going to do this is we're going to remember, okay, even though these P1 and P2 are points, we can say, oh, well, the origin is maybe like out here somewhere. Okay. You can think of P1 and P2 as vectors themselves, right? If P1 and P2, if we're thinking of them as vectors, what is this blue vector here? If we're thinking of these two vectors, how do I get this blue vector from these 2 vectors? Think back to what we learned about yesterday. Okay. If I have 2 vectors and I want to go from the tip of one to the tip of the other, what's that vector? Subtraction, yeah. So yeah, it's the difference, right? P1 minus P2, or P2 minus P1. The one I've drawn here is technically P2 minus P1, but P1 minus P2 would also work, right? So just remember the subtraction always goes, so P2 minus P1 goes from P1 to P2. So it kind of flips a little bit. And I drew some pictures yesterday that should help with that. But again, I could have used the blue arrow going in the other direction, and that would have been P1 minus P2. That would have worked out. And that'll lead us to another comment that I'll make after I work with this. But that means that to get the vector here, all I want to do is subtract these 2 points. So all I'm going to do is, maybe I'll say, first of all, think of these as vectors based at the origin and subtract. Okay, and I do this, and that gives me 4, 3, 0, right? So 3 minus -1 is 4, 3 minus 0 is 3, 2 minus 2 is 0. Okay, so now this gives me my vector. And now because I subtracted in this order, this is the vector going, this vector goes, so V goes from -1, 0, 2 to 3, 3, 2. So I should probably base it at -1, 0, 2. Now we're going to learn that it shouldn't the element be 4? Which element? No, we're subtracting. Oh, there's a -2 there. Yeah. Yep. Ooh, you guys are good at catching my typos, which is good because it means you're paying attention, but bad because it means I'm making a lot of typos. So yeah, so that should have been a negative there, which means minus negative, so it should have been a +4. Yeah, good catch. In any case, we have this vector which connects these points in this direction, right? Because of that, we should probably base it at this. It turns out that it's not actually going to be too important which point we choose once we have the vector, okay? But in this case, just because conceptually based on this picture I drew, this would be P1 and this would be P2, right? Because I did P2 minus P1. That's what I drew here. And so I should base, so the point I choose should be P1. So it should be, basically I'm starting at P1 in the V direction, okay? And so then I can just write that here. So then L of T, let me change color. L of T is, right, so -1 plus 4t, and then 0 plus 3t, and then -2 plus 4t. And that there is our parametric equation for the line. Yeah, that's not gonna work. Okay. Yeah, so someone's asking why I used this point here instead of this point here. So based on my picture here, right, this vector I chose must have been P2 minus P1, right? Because that's what this vector is going from P1 to P2. And since I want since the arrow's coming off of this point, I should use P1 here. And now based on the subtraction I did, this must be P2, this must be P1. So this is P1. It doesn't really matter which choice you make. It ends up not mattering. But I will point something out here. So technically a lot of these choices we made in it. So like, for example, it doesn't matter which way we subtracted them. We actually could have subtracted them the other way. Doesn't mean we get the same answer. It's just that there are many parametric equations for the same line. So you could take the same line and come up with different parametric equations. So if you do this and then your buddy does this and you compare answers and the parametric equation you end up with is different from your buddy, doesn't mean either of you are necessarily wrong, okay? You could still both be right, even if you get different parametric equations. Right, so again, I was very careful and said, okay, so the arrows coming out of P1, so I should make sure I choose P1, but it actually doesn't matter because if I just scooted the same vector down here, it would still be pointing in the correct direction. Also, by doing the subtraction in the other order, generally subtracting would give you a different vector, but it would just give you negatives for all of these, which just basically means the vector would be pointing in the other direction, but it would still be going along that same line, right? So because it's still going along the same line, we're okay with that. Okay. I chose P1 as this one for no real reason whatsoever. Like you could have chosen it the other way. It really is just a matter of how you choose to do it. I flipped a coin in my head, if you will. Again, it's going to give you a slightly different answer in terms of the numbers you get, but it's the same line. So if you like do some online graphing calculator that can do 3D and you graph this, you'll get the same thing. Cool. Other questions? You guys are asking good questions. What am I doing on time? Okay. Okay, I think this is the last kind of, yeah, this is the last thing I want to cover for this section, and then we'll move on to section 1.2. Okay, so we talked about lines in either R2 or R3, but now we're going to talk about planes in R3. So you could think what we're trying to do here is, and there's some nice pictures in the textbook too, but if you have basically, you have, three-dimensional space, which you can see here. You can put planes inside. Think of it like a piece of paper, right, living inside of R3. That's like a plane in R3. And basically, you need two vectors to decide what where the plane is. Now, I will say that this is just this equation that I have in front of you right now is just for planes. I should say this should be planes through the origin. Through the origin. So all of the planes that you cook up through this process are always going to be through the origin. You might be thinking like, how does only two vectors determine a whole plane, right? Because I think intuitively, you would need 3 points in order to figure out what the plane is on. But you also get the origin. The origin is always going to go through here as well. Now later, as the quarter goes on, we're going to learn different equations for planes as well. Okay. So let me do a quick example here of this plane, the idea of a plane through the origin. So I mean, basically at this point, it's just a matter of plugging into the formula, but basically you're going to be given two vectors, the plane spanned by, let's say 1, 2, 3, and 101 is given by, so again, we have this version of the equation, right, which you could then interpret as kind of an XYZ sort of situation again, right? So we can have, right, X is equal to S times 1 plus T times 1. Y is equal to S times 2 plus T times 0. So that's 0. And then Z is equal to S times 3 plus T times 1. So basically what we're doing is we're setting up our XYZ, and then each of them, the S coordinates, the coefficients on the S are going to be this vector here, and the coefficients on the T are going to be this vector here. That's kind of how we're setting this up. If you set up your XYZ, you could again, this is just me using this XYZ notation. That's a common way to do it. You can also do it. You can just if you rewrite this as an ordered pair, or an ordered triple, I should say, XYZ, right? This comma this comma this. That's just L of S comma T. So that's kind of how we do it. And again, this is a parametric equation for a plane, but this time it has two parameters. Okay. Yeah, so that's the plane. The plane is less of a focus on it. The line stuff I think is a little more important, and we're going to talk more about planes later in the I think later in this chapter even. Definitely next chapter though. Cool. Any questions? Okay, so yeah, so today we're going to talk about inner products, length and distance. So this was the warm-up problem, was trying to get us in the right headspace to think about this sort of stuff. And some of you were already getting the answer for that warm-up problem, which is awesome. But let's talk about, let's kind of talk about it a little more formally. So yesterday we learned how to add two vectors, right? We learned that if you take a vector and a vector, you get a vector, right? You can just add each coordinate. And in terms of the geometry, this was just, right, like the head to tail sort of addition, right? right there. And then you can also scale, multiply a vector by a scalar. So a number times a vector gave you a vector, and this was just stretching or squishing or reflecting also, right? Then if you do a negative number, that's what it meant geometrically. Now today we're going to learn how to basically multiply two vectors. Now I put multiply in quotes because it's not exactly like the multiplication we know, because when we added two vectors, we added a vector and we got a vector. But today we're going to learn how to multiply two vectors, vector and then dot vector. And we're not necessarily going to get a vector out. We're not going to get a vector out. We're going to get a number. Okay. And the geometric meaning for this one is a little more complicated, and so we won't completely get, well, we will get to it today, but it's not as like easy to see as these over here. These, it's like very like, oh yeah, it's just like head to tail or just squish it or stretch it. This one here is a little more complicated to see. Okay, so we're going to learn about this today. It's something called the inner product, we'll see here. So again, see this. We're going to take the inner product of two vectors. So we have this vector that we call A and this other vector that we call B. Okay, the inner product of these two. Basically, it's going to start off very similar to when we were adding two vectors, right? We just went coordinate wise and we just said add this to this one, add this to this one, add this to this one. We're going to start very much like that. So we do A1, maybe I'll make this a little skinnier. A1, B1. Then we have A2, B2, and A3, B3. But instead of making this a vector, we just add them all together. So we're just adding these together here. So that's why we get a number, because we take these two vectors and then we take their coordinates, multiply the corresponding coordinates, and then add all of those things together. That's going to give us just a nice, just one number. Okay. Okay. And again, this is one of these formulas that at first it just seems like I just made up a random formula and I'm making you guys learn it, right? But we're going to see that does actually have some kind of like geometric interpretation, some geometric meaning behind it, and also it'll have some just some more useful information than maybe it appears. At first, it just kind of seems like, oh, you just a random formula, but I promise it will get more interesting. But to start, we're going to like kind of practice actually using it. So let's do some examples here. So maybe we say, what is, so again, I did, here's my favorite sentence again. I did this in 3 dimensions, but it also works in 2 dimensions, right? So for example, I could do 1, 2, dot 3, 4. And this is going to be 3 plus 8. So that's 11, right? So I took these two vectors and I came out with a number, right? So I did this 1 times this 3, and then this 2 times this 4, and I added those things together. Okay. Cool. Maybe some more enlightening examples. For example, if I did 1, 0 times, let's say 2, 1, what's going to happen? Well, basically this 1 and this 2, I just get 2, and then I add 0 to it. Basically, the fact that this was 0 means that nothing mattered that we plugged in here. We could have put whatever we got, and we get the same dot product here, which is 2. Okay. Cool. Okay. And then naturally, like they always like to up the ante. So for example, they can sometimes they'll say things like find a value of x, which makes certain things true. So one I think they did is if I did 1, x, and then I did maybe 3, 4. I said this is equal to this is equal to 7. So then what is x, right? Okay. And in this case, we'd just kind of work kind of backwards, or not backwards, but we'd like spell this out. So we'd get 3 plus 4x equals 7. And now we can just solve for x. Okay? X has to equal 1. Right? So what that is I just did the dot product. So 1 times 3 is 3, x times 4 is 4x, and then the 7 was already given. So just kind of this is the straightforward way of doing it, right? It's just you give you 2 vectors, you figure out what the number needs to be. Just like 1 degree higher than that is, well, now instead of giving you 2 vectors completely and figuring out what the number is, we'll give you part of the 2 vectors and then the final number, and you have to figure out the missing parts, right? You've all been taking math classes for long enough to start to see kind of how we do things, right? We give you the basic formula, teach you the basic way to use it, and then start teaching you, okay, how can we use it in slightly more creative ways? Okay. Cool. So far, so good. So far, it's just like a matter of computing things, right? Like if I give you 2 vectors, you can compute the inner product, and maybe, upgrade it a little bit with problems like this. Okay. Cool. Again, if you have questions, feel free to ask. Okay, so let's talk about a little bit more vocab from this section. So this is when we're going to talk about the length of vectors. Now, the length of a vector goes by many names. So in the book, they like to call it length. You also sometimes will hear the norm of the vector. This gets confusing because later we're going to learn about something called normalizing. And then later in the quarter, we're going to learn about something called the normal vector. And those all mean slightly different things. And so because of that, we want to, this one can kind of get confusing, but this is the norm of the vector. And then this is also called the magnitude, right? Remember day 1, or I guess yesterday, we talked about how vectors are objects with direction and magnitude. This is kind of this is how you actually figure out what the magnitude is, right? And the notation for this is you use, it's like absolute value, but like super absolute value. You use double absolute, it's like absolute value. And the formula for this, some of you figured it out this morning. So basically, if this vector is given by like these coordinates v1, v2, v3, again, I'm doing this in 3 dimensions, but it could work in 2. It works exactly the same in 2. This is the square root of v1 squared plus v2 squared plus v3 squared, right? Now, what famous theorem are we using to figure this out? Like, how could you have figured this out without me telling you? What famous theorem? Yeah, Pythagorean. Yeah, no one knows how to spell it, right? I don't think I know how to spell it, but like, it's this old Egyptian guy, I think, came up with this thing about triangles. But basically, it's clear in 2 dimensions, right? For example, if I have a vector that looks like this, if this is my vector v, then I break it down into, this is v1, and then this is v2. I guess the lengths of these, and then this is obviously 3 and then 2, right? And so then this becomes my right triangle, and I do this squared plus this squared equals this, the length of this squared, and so then I just take the square root of that. Okay, so it's just this like triangle, and then adding a 3rd dimension doesn't change that in any way, right? So basically it's harder to draw the picture, but adding a 3rd dimension, if v was like coming out, you just basically look down at what's the shadow that's happening on the xy plane. You'd use this Pythagorean theorem, and then you'd add the fact that it actually goes up in the z direction, and then you get this extra coordinate here. And we'll learn in higher dimensions too later that we can have even more things here, and it just keeps going like this. But okay, cool. Any questions on this length, this norm thing? So earlier people were saying 5, right? It was the vector was 3, 4, so its length was 5 because 3 squared plus 4 squared is 25, and then you take the square root is 5. Okay. So now distance here, the distance we're going to talk about between points, but we're going to think of those points as being endpoints of certain vectors. So for example, if I want to compute the distance between these 2 points, actually, let me draw this kind of off to the side over here. Actually, I think I'm gonna do this a little closer. If I want to draw the distance between 2 points, well, I say, okay, well, where's the origin? Let me think of these 2 points as vectors. Okay. So this is maybe B, and this here is A. Okay. Well, if I want to think of these 2, once I think of these 2 points as vectors, I can compute the distance between these points by, well, first of all, I can cook up a vector that connects these 2 points. What's that vector here? If I have these 2 vectors and I want to connect their tips with a vector, what's the vector that does that? So basically, what is this vector here? Again, going back to the stuff we learned yesterday. Some people are saying A plus B. Someone's saying A minus B. A minus B is closer, but not quite right. B minus A. Yeah. So this is what's gonna take you, you're inevitably, and this is gonna be what your big mistakes are at the beginning. It's little things like that. It's making sure that you remember which way it goes. So we're going from A to B, and so we do B minus A. Again, you just have to remember that. I think the easy, well, maybe not easy way to do that. Maybe I'll come back to that in terms of how to remember A minus B. I drew a picture yesterday that might be helpful, but you might want an easier way to think about it without having to draw a bunch of pictures. Okay, so we have now this vector. So now we can just compute the length of this vector. So the distance between endpoints of A and B is the magnitude of B minus A. Okay. And this is the distance between these points here. So you can come up with the whole formula for that. So it's the difference between A1 or B1 minus A1 squared plus B2 minus A2 squared plus B3 minus A3 squared. Okay. Now, because of the way I drew the picture, I chose it was B minus A, but I could have drawn the picture the other way and A minus B would have been correct. And what you'll notice here is we're subtracting numbers, but then we're immediately squaring them. So if we switch the order how we subtract them, right? All that happens when you switch the order of a minus sign is you get an extra negative, right? And then if I have an extra negative and then I square it, that negative goes away anyway. And so that's basically what that means is that, so maybe I'll make this a note that B minus A is equal to A minus B once I have the norms around it. So, B minus A is not necessarily the same as A minus B, but they differ by a minus sign. And so by taking the norm, the minus sign goes away. Cool. Any questions? Okay. So norm is just for computing the length. You can also think, I guess, maybe a neat thing to notice here is that this is just the square root of the dot product of v with itself. So I probably should have said this sooner, but this is the reason this is in this section about dot product is that this is how you can think of the norm. You just take the square root of the dot product, right? So v1, like if I take the dot product of this vector with itself, then you get v1 times v1, which is v1 squared, plus v2 times v2, which is v2 squared, and v3 times v3, which is v3 squared. So you can think of this in terms of the dot product here. So we're already starting to see something to do with, okay, this is a slightly more useful way to think about to use the dot product. The dot product of a vector with itself is the length, is basically the length once you throw a square root on there, right? Okay, so that's a nice interpretation of the dot product, but in general, the dot product has two vectors involved. So what happens when we get different vectors involved? And we'll see that in just a second. Okay. So the next thing I want to talk about is unit vectors. Okay. A unit vector is nothing super special. So the word unit means one, right? So a unit vector is just a vector that has length one. Okay. So some examples that we'll see off the bat is these vectors, the standard basis vectors that we talked about last time. Right? This is 1, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right? So those all have length 1 because you just get 0 squared, and 1. You add those together, get 1, take the square root, you get 1. So these all have unit vector, but maybe we can come up with some some more exciting examples. Something like the square root of 2 plus the square root of 2. Did I do that right? No, that has length 2. So I need to divide by, actually, 1 over the square root of 2. That's what I was thinking. Right? If you remember, like unit circle stuff, basically anything, any coordinate on the unit circle is going to work here. That's why it's called the unit circle, and these are unit vectors. Okay. Cool. Right. So this is just again more vocab to throw at you, extra little words that we can use to kind of describe certain situations. Okay. And now here, you know, I mentioned earlier that the length is sometimes called the norm. Now we're going to learn something called normalizing, which is not exactly related. And so that gets a little confusing. But to normalize a vector means to take that vector and get a vector in the same direction, but making sure that it has length 1. Okay. So the formula for this is you take v and you divide by its length or its magnitude. Okay. And the notation we sometimes use is v with the little hat. This caret on top of a character, we usually call that a hat. So this is v hat, which looks kind of trippy with a v because it's like the same symbol upside down. But you just, this hat means that you basically, if you have a vector v, v hat is that same vector, basically points in that same direction, but if that vector is super long or super short, you just normalize it so that it's just a unit length. It's exact, you know, it's exactly 1 length away. And you can double check that this, like no one ever actually does this, but the norm of this is always going to be 1, no matter what vector I plug in, except for 0. You can't plug in 0 here. So it says non-zero. Okay. Okay, cool. Any questions so far? So far, I haven't done much. I've just been kind of like introducing concepts without necessarily doing examples. Okay. So 1.1 was kind of an exception, I'll say, because we have like the quiz. The quiz is happening for that right away. But after this, like basically you're gonna have time with this material before you get to the quiz and the worksheet. So you're gonna have, I would definitely suggest working on the homework and stuff leading up to things and trying some problems. And then if you don't know how to do them, that's when you come to me or Matt for questions. Okay, someone's asking what these double, so these double absolute value things mean are the norm, the length, right? So that's what this is the definition right here of this notation. Okay. It's just the square root of all of this stuff, which is just the length of a vector. Okay, cool. Okay, and then a unit vector is vectors specifically which have length 1, and then you can turn any vector into a unit vector by using this formula. Cool. Okay, so the next thing we're going to talk about is angles between vectors. In R3, it also works in R2, but does it work in R2? Yeah, it does work in R2. It's just a little more interesting in R3. So you get this relationship here between the dot product, the norm, and the angle of between the two vectors. So this here is really the geometric interpretation of the dot product. This is what the dot product means. It gives you the angle basically for free. Or I shouldn't say for free. There's a little bit of work here, right? So you have let theta be the angle between these two, and blah, blah, blah. So basically, you might think like, okay, but this is like a complicated formula. How do I actually go about getting the angle from this? What if I want to find the angle? How can I actually use this? Well, you can basically solve for theta in this situation, and you can get that theta is equal to cosine inverse of A dot B over the norm of A times the norm of B. Okay. Cool. So one thing I'll notice is like, let's go back to like our pre-calc brain and remember like cosine inverse. Right, this is cosine inverse is not 1 over cosine, right? It's arc cosine. So maybe you prefer, instead of this, you prefer seeing arc cosine, right? So there's like these two ways of inverting your trig functions. One of them was inverting as in reciprocal, which is that's when you get like cosecant and secant and cotangent. But this is not that. This is inverting them as functions, which is when you get arc cosine, or if you were doing sine, it would get arc sine and stuff like that. So this is inverting it as a function. Now, if you remember a little bit about the arc cosine, does anyone remember what the range of arc cosine is? So remember that cosine takes in any angle and will spit out a number between -1 and 1, right? That's what cosine does. So if arc cosine, it's going in the opposite direction. Arc cosine will take in any number from -1 to 1, and it'll spit out, some people are saying it spits out something between 0 and pi, right? So the range of this, so theta is always going to be, because it's coming out of an arc cosine function, it's always going to be between 0 and pi. Between 0 and pi, right? So if you are more graphically minded, right, in general, the cosine function, you can't cook up an inverse of the function as a whole because it kind of goes back up and down. But if you just restrict to just this part here, then now you have an inverse, right? If this is x, then this here is arc cosine of x. And hence that's why it's always between 0 and this here is pi. Okay. So all of this to say is that this formula is only going to give us angles between 0 and pi. But you might be thinking, well, I know vectors. and they can live in like space all weird. What if the angle is bigger than pi? What if will this formula still work? Well, if you have a vector, let's say this is A. Oh, I forgot my little hats. Okay, so say I have A, and let's say this angle goes past pi, something like this. This is B hat. Okay, this is bigger than pi. This formula didn't work because this angle's bigger than pi, and this thing can only give me something up to pi. What happened here? So anytime you have two vectors, I was looking at this angle, right? But there's another angle here too, right? This angle over here, right? So the thing about this formula is, so this angle now is smaller than pi. Remember, pi is 180 degrees. So this was, even though this angle was bigger than pi, this angle over here was smaller than pi. So the thing with this formula is it's always going to give you the smaller of the two angles, right? Anytime you have two vectors, there's two angles that correspond with it. There's like this big one and then this smaller one, okay? And this formula here is always going to give you that smaller angle, okay? Just a little observation. Okay, any questions? Okay, we've got 5 more minutes. I'm gonna hopefully get through this section. I don't remember how many slides I have left. I might not get through this whole section. I'm gonna try to get through this slide at least. Okay, so we now have a way of talking about angles between two vectors. It's this formula, which I admit is not the most beautiful formula in the world. It can be kind of messy, especially when you actually start to try to do some computations with this and compute some angles. But at the end of the day, if I give you two vectors, I'm not asking you to do this all by hand necessarily, right? Like this part right here is a type of thing you might plug into a calculator, assuming you don't get a nice number here, right? Like if you got 0 here, then hopefully even from this picture, you should be able to figure out what theta is if I got 0 here, which is actually gonna come up in a bit. But in general, yeah, this is the type of, the arc cosine is the type of thing that you plug into a calculator, right? So at the very least, it's like, okay, this is now like a problem that like if I give you two vectors and I tell you, give me the angle between them, this is a formula that can do that for you. Okay, you now have a formula then that can do that for you, right? And it's all related to the dot product. So some people would argue that an inner product, or I don't know if I made that clear, but the inner product is sometimes called the dot product. I wrote it here, but I don't think I said it out loud. I will use the phrases interchangeably. So if you have been confused by that, I'm sorry about it. I should have mentioned it sooner, but the dot product here is geometrically, it's related to the angle between the two vectors. And this is the formula that showed you how they're related. Okay, cool. So to finish off today, and then next week, tomorrow, we'll finish up this section with just one more slide. And for today, the last thing I want to mention is what it means for two vectors to be orthogonal, which is a new vocab word, which just means that their dot product is 0, okay? Which may not seem like anything special. It's like, okay, well, the dot product can be a lot of things. Why is it special if they're 0? So let's figure out what that means geometrically. And the way we're going to do that geometrically is we're going to use this formula here. So if, maybe I'll use color here. So if the dot product of these two vectors is 0, then this, by that formula, the product of the norms times the cosine is 0. So now if we're multiplying a bunch of things, then and getting 0, then one of the things we're multiplying has to be 0. So we can get that, like, okay, maybe one of these vectors is 0 or has length 0. So one of these things happens, which is not super interesting, right? Like, okay, you just had secretly one of these vectors was just a point. It didn't have a whole, was just, or sorry, I should say, it was just the origin. It didn't have any length. Okay, so that's less interesting. More interesting, so I should say, or here, this happens, or this happens, or the more interesting case is when cosine of theta equals 0. Okay. If cosine of theta equals 0, then what is theta? Remembering that theta, we want something between 0 and pi. Not 1. So remember, theta should be some angle, right? Someone's saying 180. Yeah, pi over 2 is the right one. So you guys had some good guesses. I keep writing the word because I see it in the chat. Pi over 2. Again, this goes back to, if we look at this picture over here, if x is equal to 0, that means we're right here. So that means arc cosine of x is 0, is pi over 2, halfway between 0 and pi. Or 90, in other words, 90 degrees. So orthogonal is in vector land is basically just a synonym for perpendicular. Okay, so we have a new word for perpendicular. Typically is talking about lines. If we're talking about vectors, then we say orthogonal. Okay, but intuitively that's the same thing. They form a 90-degree angle. They form a right angle. Okay.